computer. Okay, here's 2330. Announcements. Okay, we're going to continue on with chapter 2 today, which is acids and bases. And then we might even get in a little bit to chapter 3. Note that if you follow the lecture schedule on Canvas, we are right on task, so that is great. Number 2, labs start next week. If you are signed up for the lab, it's not a requirement. If you are signed up for the lab, they do start next week. That is Wednesday, February 3rd. Okay, so you should be getting your laboratory notebook together for that. The first lab is actually laboratory safety. Okay, so I've talked to both of your instructional assistants, and they one has actually taught the online section last semester, and we have some improvements to it from all the difficulty we had last time. And the live sections, we have 2 live sections, and they will be taught as well live on campus. So if you're in those sections, there's only about 9 of you there, but good. And we will have a really good selection of experiments to do this year. Okay. So does anybody have any more questions about the lab? It starts next week. Get your lab notebook and read laboratory safety, which is the first experiment. Notice that the Canvas site has gone live. Okay, so the Canvas site has gone live. And this is where we will be submitting all of our materials, all of our pre-labs and post-labs. The online people will be doing the quizzes online as well. And I will send out an email on how to do that. It'll be quizzing through Canvas. The live students will actually take handwritten exams, and those will be put in by your lab instructor. Okay, so okay, there will be a Zoom link. I have talked to the lab instructor. Again, we will have a Zoom link for all of the live, for the 2 different sections, online sections, and they do meet at those specific times. So what'll happen is at that assigned time, your lab instructor will come on, give you your Zoom pre-lab lecture, and then send you off to take your quiz and go ahead and do the online lab, which is found on, well, it's really found on YouTube. I will liberate those videos as we go. And so there'll be a video portion of the lab. There will be and then there is the pre-lab and post-lab, which you'll upload to Canvas, and I'll give you instructions on that as well. But it all starts next Wednesday, okay? So look for an email starting approximately sometime this week or maybe Monday to tell you that. How do you know if you are online or in person? Your section, if you go to your schedule, it should say whether it's arrange for location, means you're online. If it actually has CHEM 229, that means you're live. Okay, so there's only 2 live sections, and I believe they are section 251 and 252 are the live sections, and sections 301 and 302 are the online sections. Okay, so I think that does the lab last the entire block of time as stated? A couple of them do last the entire time. Most of them don't last the entire time. The online section, you're actually just going to be online for the pre-lab lecture and answer questions. And the rest of it's done at your leisure using YouTube and uploading. Okay, I will send out an email saying whether or not you are in the live section or the non-live section when I send it out. And so I'll separate into 2 emails so that you know. The live section is not broken up into an A-B. You go every single week. Our section is small enough that we get to do all 10 procedures. And so there will not be an A-B. You will go to lab each and every week unless you test positive for COVID, then you stay home and do the online version. Okay, does that answer the question? Is there a way for do this? Not live experiments outside of lab, but you can do the quote online experiment anytime you want, as soon as the video sets up. So I think the video set up that day, the week of, so you can actually watch the online video and do your post lab ahead of time, and they'll be due at midnight on Wednesdays. Okay, I think that answered all the questions on there. Does the lab use this? Okay, so look for those emails on Monday at the latest. I'm going to try to get them out by Friday, but Monday at the latest as to who's live and who's not, when you're actually scheduled to do it, and what the instructions are. Remember, all assignments are uploaded to Canvas. All online quizzes are done on Canvas. Live quizzes are done in person. Okay. But everything needs to be submitted to Canvas as a PDF or some kind of image for grading. All right. All right. No more questions in the chat. So is that good? Okay. Well, what I will do is I'll go ahead and we'll continue on with chapter 2. I, again, figured out how to get my iPad back to communicating with my computer by a cable. And so it makes it much, much easier to, it takes much less bandwidth and it's much less jumpy. I did a whole lecture this morning and it worked out really well with no jumpiness at all. All right, so what I'm going to do now is I'm going to share my iPad with you. And you can follow along with either the slides on Top Hat or if you download the slides from Canvas. Okay, so I've put my gallery view up over here. And just to make sure that I'm not lecturing just to cats, I actually have live people there, so that's great. Okay, so we talked about acids and bases and that we had some old-fashioned acids and bases. The original meanings were things that dissolved in water and made hydronium ion or hydroxide ion, right? And those were the Arrhenius acids and bases, and they required water, okay? But we don't use water very much in organic chemistry, so we started talking about a different definition of acids and bases. And so a Bronsted-Lowry acid and base, occasionally denoted Bl, is a proton donor. So if it gives away a proton to something else, it is an acid. If it accepts that proton, it is now a base. But that means that if you were an acid and gave away a proton, you can now accept one. So you become a conjugate base. And if you were a base and accepted a proton, you now can give that proton back and you are now a conjugate acid. So this pairing is very important to understand how the equilibrium of acid-base reactions works. You have an acid and then it converts into, on the other side of the equation, the conjugate base. And your base converts into the conjugate acid. Now, how do we know which way things are going? So that's where we have to think about what does it mean to be a strong acid and what does it mean to be a weak acid? Sorry, preemptive green tea strikes, I don't cough. Okay, so if we take a series of these acids and put them on a continuum, okay, we're going to start to see a kind of a trend we have here. And so this is something to look at. So if we think about our classical acids from inorganic chemistry, from Gen Chem, we see that we have HCl and HI, the acids made with halogens. But then we also have sulfuric and nitric, and those are very, very strong acids. And then we have phosphoric. Okay, so these are what we would call typically strong acids, and we'll talk about the definition of strong in a little bit. But then we have a continuum. There's some things that aren't as strong. So the first organic acid we're going to talk about is this is this one right here, acetic acid. Okay, so it's an organic acid, it's a carboxylic acid, and so we're going to look at that as one of our starting points for acidity in organic compounds. Okay, so it's the most acidic organic compound we have. But as we go down the list, we can go to other things like, look right here. We have something right here, it's called phenol, okay? So it's like a aromatic ring with an OH on it. And it's acidic too, because that proton can come off. But then we go up a little bit more and we have water, and this last one right here is ethanol. So water, which is inorganic, has a certain amount of acidity to it, and alcohols, which are organic, are similar to water in their acidity. And so what we're going to see is this continuum of that. Now, When we have a strong acid, it has the proton on it. When we lose that proton, it becomes the conjugate base. And in this case, notice all of these are ions right here, specifically negative ions. And so our conjugate bases tend to have that negative charge. Not all of them. Some of them, like ammonia, can be neutral, but most of them have that negative charge. Okay, so HI will become iodine in its conjugate base. Acetic acid will become acetate ion in its conjugate base. Phenol will become the phenoxide, and ethoxide and hydroxide will be the two others here. Why is this important? Okay, so because we're looking at water as a weak acid and these others as strong acids, we have a continuum which we can compare and contrast. And in nature, we always want to go from the strongest acid to the weakest acid. So now we have a driving force for converting from one acid to a conjugate base because of that driving force. Okay, so what's interesting about that is that once you have a strong acid, okay, in this case here, this HI here, and it becomes a conjugate base, it is now a weak base. So strong acids become weak bases. Okay, that's an important concept to have. Now, weak acids become strong bases. Let's think about that. If I have a strong acid, I'm really easily ready to give away my proton. So that means when I'm in my base, I'm wanted to give it away. Why do I want it back? That makes me a weak base. In this case here, where we have a weak acid, I didn't want to give that hydrogen away, but something more basic than me was there and therefore took it away. And so now that I really want that hydrogen back, so I become a strong base. Okay, this juxtaposed continuum here is very important in the idea of which way an equilibrium will lie in an acid-base reaction. Strong acids become weak bases, weak acids become strong bases. Okay, so let's do one other thing. Just like in regular acids, you can have more than one proton transfer. Okay, so we have to think about that. An acid can be positively charged, neutral, or negatively charged. So in the case of something like carbonate, right here, we start out as a neutral molecule that gives away a proton and becomes an anion. In the case of hydronium, we already have a proton to give away, so it's a stronger acid. And in the case of phosphoric acid, if we've already given one of those hydrogens away, we still have the possibility for giving two other hydrogens away. So acids can be positive, negative, or neutral, okay, depending on how many protons are available to transfer. Bases are almost always negatively charged, except for ammonia, which is also neutral. And acids can be classified as monoprotic if it only has one hydrogen to transfer, like in HCl. Diprotic if it has two hydrogens to transfer, like in carbonate. And three or triprotic if it has three, like in phosphoric acid. Okay, so the thing is that each proton coming off has a different acid strength. So the first proton can be a strong acid, then we have the next one, and then we have the last one to come off. And they are getting weaker and weaker acids as they come off. Okay, so let's use carbonic acid as an example about that proton transfer. So carbonic acid is basically it all CO2 and water, and it creates carbonic acid. Okay. The first thing it'll do is try to transfer one of those protons to water to become the hydronium ion here, and the second one is going to stay on that, making that negatively charged conjugate base. Okay. However, this particular conjugate base has another proton to transfer. So it can transfer that proton to the water, making us a dianion. Now we have carbonate ion. And notice there are no other hydrogens there to give away. Hang on, I gotta let somebody into them. There we go, admit. And now it's transferred both of its protons away. So it had one step where it gives one proton away, and the second step where it gives its second proton away. Okay. So in this case, this is your acid and this is your conjugate base. In the second case, this is now your acid and this is your conjugate base. So notice that it came from one side of the reaction to the other. When it came to the side of the reaction where it's giving away its proton, it is now the acid. This is now the base, and we've transferred it. So just because it's given off one proton and is a conjugate base in one side of the reaction, it can be a conjugate acid. It can be an acid on the other side of the reaction. Okay? So that's important to understand the concept of, can it give or take a proton? Now notice that if we had it on this side of the reaction, if we had the carbonate here on this side of the reaction and it accepted a proton, it would be the base accepting a proton to become the acid. So it goes, that's why there's those double things there. It's in equilibrium, it goes back and forth. Okay. All right. So that gives rise to that inverse relationship between acid strength and the strength of the conjugate base. Strong acid, weak conjugate base. Weak acid, strong conjugate base. All right, so now let's get to a definition of what a strong acid is and what a strong base is. Okay. So technically, a strong acid is one that completely or almost completely gives away its hydrogen when it hits water to form hydronium. Okay, so we think of the classic ones like hydrochloric acid, hydrobromic acid, hydroiodic acid, so the halide acids, plus nitric, sulfuric, and perchloric. Okay, those are our six strong acids right here. Our strong bases are those that produce our hydroxide ion when it goes in there. And the most common ones of those are the ones with the metals associated with them. Okay, so those are what we call strong acids and strong bases. So they almost completely dissociate into their ions in water. Okay, so if that's what a strong acid is, that means a weak acid only partially dissociates in water, meaning that instead of having an arrow going one direction and one direction only, we have an equilibrium. Okay, so some of it is existing as the acid in the solution. Some of it is existing as the conjugate base in the solution. So that's when we have a weak acid. It's not completely one way, and there is an equilibrium in the system. Okay, that's what the double arrow thing means, equilibrium. It's going back and forth. Now, for a weak base, it's the same thing. It only partially dissociates in water. That means if we mixed ammonia and water together, we would actually be able to detect the ammonium cation, the hydroxide anion, water, and free ammonia by itself, because it doesn't completely go to one or the other. It's somewhere in between, and all four species are found in that solution. So that's the difference between weak acids and bases and strong acids and bases. We have that equilibrium. All right, so how does that help us? Well, we need to think about it as, okay, now that we had an acid and it lost a proton, it's now a conjugate base, right? So we have to figure out which way the reaction lies. So if we have our acid here and we have our base here, and it loses a proton to our base, we now have our conjugate base and our conjugate acid. We have to look at the strength of this conjugate base and compare it to the base, or we have to look at the strength of the acid and the strength of the conjugate acid. If we compare the acid to the conjugate acid or the base to the conjugate base, we can tell which way the equilibrium lies. Okay, and because there's an equilibrium there, we can actually calculate out what that equilibrium constant is. So if we had our equation set up this way right here, and we took the concentration of our acid times the concentration of our conjugate base over the concentration of the original acid. And since water is usually excess there, we kind of take that out of the equation. And when we do that, we end up with what we call a Ka, which is an acidity equilibrium constant. Okay. So basically, we're comparing the concentration of the original acid, the conjugate acid, and the conjugate base. Okay. By comparing those ratios, they will naturally reach a certain equilibrium, and by measuring them, we know what that equilibrium constant is. When we know what that equilibrium constant is, we know which direction that equilibrium lies. Okay, so we have that equilibrium constant Ka. Ka numbers can be very large. So in general, what we end up doing is taking the log of the Ka, and that's what we call the pKa. Okay. So instead of having thousands of numbers and or a million or negative a million or something like that, we actually take the log of it and it turns it into nice, easier to handle numbers. Okay. So the classical definition of a strong acid is any acid with a pKa of 0 or below. Okay. So that means somewhere right here between phosphoric acid and hydronium ion is that break point between strong acid and weaker acid. Okay. Now, this pKa right here, notice the pKa is negative. So when pKa's are negative, that means we have a very, very strong acid. Okay. Now, if our strongest acid here is at -9, how weak an acid can we go? Well, let's look. We can go all the way up on our scale to 51. We can get around 55 for a couple things. But let's look at what's happening here. The first organics we have here are the, are the carboxylic acids. Those are the most acidic organic compounds. And we see them here in the 4 to 5 range. Okay. The next most is this phenol right here. But then we have water and ethanol right up here at 15. Okay. So the key you're going to want to do is you're going to want to remember a few of these numbers, like that those acids right there are strong acids and are usually negative. The key ones you need to look at are acetic acid. You need to know what the relative strength, you need to know that it's 4.7. You need to know water and ethanol, and then you're going to know some of the hydrocarbons as well. Those are the ones you really need to pay attention to. We will talk about the phenol as well later. Okay, so water is right here around 15.7. Ethanol is about the same. And then when we go up to the hydrocarbons here, that hydrogen bonded to carbon actually is acidic. It's very poor. It's a very, very weak acid, but you can pull that hydrogen off. And that's why we have this pKa value of 51. So the higher the number, the weaker the acid. Okay, and the lower the number, the stronger the acid. All right, so how do we use that to our advantage? Okay, so we're going to use that pKa value to determine the equilibrium of an acid-base reaction. You will need to memorize certain ones like water, alcohol, ethane, and ethine, as well as acetic acid. Those are the major ones that you need to memorize. Okay, so the first thing we do when we want to talk about that is we want to identify either the acids or the bases, and we're dealing mostly with pKa. So always look at the acids, the acid and the conjugate acid. Okay, so you want to identify which of those are which on each side of the reaction, and then compare the strengths of those two, determine which of those is the stronger acid. Okay, remember that the stronger acid gives the weaker conjugate base, and the weaker acid gives the stronger conjugate base, which means the stronger acid will react with the stronger base to always give the weaker acid and weaker base. That means by looking at the pKa, the higher the number, the more likely it is to be shifted that is the weaker acid, it's going to be shifted in that direction. So let's apply this. Okay. So let's take a look at this acid-base pair. Okay. Again, I don't have the pKa's for the base right here, or this base, because we're only looking at the acids. We look at one, only the acids. Okay. And if we look at this right here, our pKa for acetic acid is 4.76. You should memorize that. Okay. But ammonia was our base. However, when we protonate it, it is now a conjugate acid. And so we can look on that table and say, oh, the ammonium ion on that conjugate acid table was at 9.24. Okay, so the higher the number, the weaker the acid. So what that gives us is that the acetic acid was stronger acid than this ammonium ion. So what does that mean? Where does the reaction lie? Does it lie toward the right where we have the ammonium ion, or does it lie to the left? There's a chat room.
To the left.
Okay, we're going to lie to the weaker acid.
Sorry, I meant to the right. Sorry.
Yeah, it's perspective. Yeah, you're looking at the weaker acid, so it's always going to go toward the weaker side. So our strong acid is going to give up enough of a proton, more protons than the weak acid will, and so it always lies on the weak acid side. Okay. And weak acid is the higher pKa number. Okay, so questions about that acid-base pair, that's important, and questions about stronger versus weaker acids based on their pKa values.
I have a question.
Yes.
What you just said, that the reaction is on the right side, I don't understand that, because I thought you said that the reaction is going to be with the stronger acid and the stronger base.
The stronger acid is going to react more than the weaker acid. So that means that we're going to have the stronger acid converting to the weaker acid. And in this case, if we looked at the strength of these two bases, which we don't do, we only want to compare the acid strength or the base strength, it turns out that this is the weaker base than this. So the stronger acid is reacting with the weaker acid to generate the weaker acid and weaker base. Okay. So we always go from strong to weak. That's the driving force. And you want to memorize that the strong acids like HCl and stuff are strong, and then start with acetic acid as our first, water, ethanol, and then we're going to do ethane, ethene, and ethyne. Okay. Did that answer your question? Always go to the weaker acid.
Can you repeat that one more time?
It always, the equilibrium always lies toward the weaker acid. Okay.
Oh, no, the
his,
list.
Yeah.
Sorry, I didn't mean to interrupt you.
Okay. So it always goes to the weaker acid. Think about this. The stronger acid really wants to get rid of its proton. The weaker acid kind of wanted to get rid of its proton. So the one that wants to get rid of it more is going to react more. So the stronger acid always gives up a proton to form that weaker acid. Okay? So now that is just for those compounds stated, but there are 4 factors that will change the acidity of a compound. Okay, and those 4 factors are the electronegativity of the atom bonded to hydrogen. Okay, so think about that. HCl, HI, HF, those are going to be the more acidic ones because those are really electronegative atoms. And most of those are considered strong acids. Okay. The second thing we're going to look at is the resonance stability of the conjugate base. Okay. What I mean by that is, can we stabilize that charge over more than one atom? If we can stabilize that charge over more than one atom, it's going to become more acidic. And I'll demonstrate that with acetic acid. The next thing we have is the inductive effect. So not the atom bonded onto the hydrogen, but the atom bonded 1 or 2 or 3 bonds away from that hydrogen. There's an inductive effect. There's can pull through those sigma bonds and change the acidity of a system. And then the last thing is our size and delocalization of charge. By that I mean big fluffy ions like iodine spread that negative charge out over a greater area than a small ion like fluorine. So even though fluorine is more electronegative than iodine, iodine's bigger. And that size and delocalization of that negative charge makes it more acidic. Okay, so we'll dig a little bit deeper into that as we go. So the first thing we have is electronegativity. So if we trend along the periodic table and look at what we have, HF to start, let me do this, HF to start has a electronegativity of 4 and a pKa of 3.5. So it's not a strong acid because it's not 0 or below, but it's not a, but it is more acidic than water. Okay. So the next thing over on the periodic table is oxygen, and it has a pKa of 15.7. Okay. It has an electronegativity of 3.5. Okay. So our electronegativity is decreasing as we go this way, and our acidity is decreasing as we go that way along that same row. By the time we get to nitrogen, our electronegativity is dropped to 3, and our pKa is jumped up to 38. Okay, so that's an even weaker acid. Okay, and by the time we get to carbon, the electronegativity is 2.5, and its pKa jumps again to 51, making it the weakest acid of the 7. Okay, so along that row, the electronegativity trend and the acidity trend are both in agreement. Okay, so this will hold true along the same group, along the same row, because they're all approximately the same size. Okay, so what else affects it? Well, I said that if you can delocalize a charge over more atoms, it's more likely to be able to spread that charge. And if we drew the structure for this acetate ion here, you would see that you have a structure that looks like this, CH3. But then there's no reason that negative charge has to be here. It can be transferred up to here, giving you something that looks like right there. And those flip back and forth continuously, which means you have now spread that negative charge out over 2 oxygen atoms instead of just 1 oxygen atom, making it more acidic. So let's compare that to alcohols, which cannot. They only have the 1 oxygen, and on the oxygen is the only place that 1 oxygen is where that charge stays. The pKa of the alcohols is much higher. The pKa of the alcohols is almost 16. So that being able to have that charge delocalized over 2 atoms makes acetic acid more acidic than water or ethanol. Okay. So that's why all carboxylic acids tend to be stronger than all of the alcohols. So here's another drawing of that resonance stabilization here. In the case of this, if we deprotonate right here, we can go to our first structure here, which has the anion on the lower carbon. In the second structure, it has the anion on the upper carbon. And notice this is going back and forth. This is not an equilibrium. This is just 2 equivalent Lewis dot structures, saying that the negative charge can be on either. If we try to draw that same Lewis dot configuration for ethanol here, we can't do it because we only have that 1 oxygen. And therefore that charge is trapped on that 1 oxygen, and therefore it's less acidic. Okay. So that is how the electronegativity affects it. This is how resonance stability affects it. So the more charge you can spread out, the greater the acidity. Okay, now that brings us to our third effect. And the third effect is called the inductive effect. Okay, so instead of being directly bound to the hydrogen that's acidic here, what we're going to do is we're going to take atoms, specifically electronegative atoms nearby, and increase the acidity by pulling electron density through the bonds. So if we looked at these bonds here, the carbon-hydrogen bonds, they are non-polar bonds because they have about the same electronegativity. And so our baseline for having this hydrogen come off is our 4.78. Okay. However, if we have that same thing, instead of having the fluorine bonded directly here, what we have is the fluorine is more electronegative than carbon. So it's going to pull electron density away from this carbon. And we have another fluorine over here, so it's going to pull electron density away, and another fluorine, it's going to pull electron density away. That carbon now has some of its electron density pulled away by the fluorines, which means it's going to be more electronegative than the carbon next to it, and it's going to pull electronegativity away from this carbon here. And when it does that, that can pull electronegativity away from the oxygen. When we do that, this becomes more electronegative and it becomes stronger, a stronger acid. So this is the inductive effect because you're actually pulling electron density through sigma bonds. So what is that kind of, how does that trend? Well, you know, it'll trend the more electronegative things you have on there, the more acidic it becomes. So going from acetic acid with just hydrogens on there to 3 fluorines on there, it gets almost down to a true strong acid with a pKa of near 0. So that brings us to our last one. And I kind of talked about this, but the larger a volume over which you can stabilize that negative charge, the greater stability that ion has. And if that ion is more stable as that large fluffy object, it makes it more acidic. Okay, so notice that in the case of these strong halide acids here, fluorine is the most electronegative of the set. But fluorine is much smaller than chlorine, which is much smaller than bromine, which is much smaller than iodine, making hydroiodic acid the strongest of the acids because the iodine is so big and fluffy. Okay? And then as the ions get smaller and smaller, so when you get down to fluorine, that's a very small one, and so it really doesn't want to give up that hydrogen at all. In fact, the fluorine-hydrogen bond is almost not, it is less polar than some of the other ones as well because of the electronegativity difference. No, it's more polar, sorry, but it's the size that's keeping it from being the stronger acid. Okay, so you would think just from the electronegativity argument that that would happen, but it's really always going to be the size. The anions are always larger than the atoms they're derived from. So because you're adding an electron to that outer shell to fill that outer shell, and so that electron cloud gets bigger. So every time you add an electron to that cloud, it gets bigger and bigger. Now, even if we compare the ratios between those, fluorine is always going to be a very, very small atomic radius. Iodine is going to be a very large atomic radius, making it more acidic. All right, so questions about the 4 things that affect acidity in those. Electronegativity directly bound to it, the size of the ion bound to it, the ability to delocalize. Okay, I have a hand raised.
So I was just curious if you add a hydrogen atom to it, does that make it more positive and therefore smaller in its shells?
Okay,
Slightly smaller.
when you add the hydrogen to it, there's 2 ways to do that. You can add it as a covalent bond. And if you add it as a covalent bond, that means the formal charge has gone to 0. So it's not an ion. Only when you remove that hydrogen is the electron left behind and it becomes an ion. Okay? So you have to think about it is when the hydrogen is bonded to it, it's sharing the electronegativity of the electron shared in that bond. So it's not an ion. So it does become bigger as you remove the hydrogen. Okay, does that make sense?
It becomes bigger as you take it away.
Right, because instead of sharing the electron in between the two nuclei of the hydrogen and the halogen, you now have to, all of the electrons are on the halogen and it actually gets bigger.
Oh, right. Yeah. Okay.
So yeah, anytime you go from a neutral atom to a negatively charged atom, it gets bigger. All right, so that's great. I mean, we're talking about a kind of acid where we transferred protons, and that's a little more well-defined in organic chemistry than the original Arrhenius definition where we had to have water, okay? But I want to introduce the last topic of acids and bases. And this is a little bit different, but it follows all of the other acids and bases follow these rules. The next thing I want to talk about is what we call Lewis acids and bases. So the Arrhenius that has water, we have Bronsted-Lowry that has to transfer a proton, and now we have a Lewis acid, and it doesn't transfer a proton, but a Lewis acid is defined as a molecular ion that can form a new covalent bond by accepting a pair of electrons. Okay, and I want to tell you that that's exactly the same as a Bronsted-Lowry acid, and I'll show you why. A Lewis base is the opposite. A Lewis base is willing to have a lone pair reach out and create a new bond. So a Lewis base, think of having a lone pair on it already, reaching out to create a new covalent bond. So a Lewis acid is a molecule coming in and forming a new covalent bond by accepting electrons. Acid accepts electrons. Base donates electrons. Okay, so let's look at that again. This is kind of confusing at first, but it starts to make sense when you play with it a little bit. Okay, so in this case here, we have our Lewis acid here, and our Lewis acid wants to accept an electron pair. Okay, our Lewis base wants to donate an electron pair to make a covalent bond. So basically, the two electrons that were this lone pair become the two electrons in our covalent bond. Okay, and in the process, we either lose charge or gain charge right there. It doesn't matter whether the species are charged or not. What matters is that those two electrons that were a lone pair are now our new sigma bond. Okay, so acid accepts electrons, base donates electrons. So let's play with that a little more. Okay, so let's go back to the original definition of the Arrhenius, right? Where HCl dissolves in water. Okay, but let's look at it in the terms of Lewis acid, Lewis base theory. Okay, so in this case here, we have a hydrogen atom that is bonded to this chlorine atom. Okay, it's got a sigma bond. It's there. However, we also have an oxygen over here with a lone pair. So that oxygen is going to donate that lone pair to this hydrogen to make a new sigma bond. Okay, so that has been accepting these electrons. Now, in the process, it's giving up these electrons back to the chlorine. So the hydrogen here is the Lewis acid. The water here is the Lewis base. And we generate our new compound here, our hydronium ion, and it's counterbalanced by our chloride ion. Do we see how this definition is more precise about acids and bases? Acids accept electrons, bases donate electrons to create sigma bonds. All right, so why is this so important in organic chemistry? It's like, well, there's a lot of things we would consider are not really acids or are very poor acids. And this Lewis acid base structure allows us to create a way in which we can analyze how things work based on their acid base strengths. So now to take it away from the the previous example, which was an Arrhenius acid, because we were reacting HCl with water, let's turn it into a Bronsted-Lowry system. So we don't have water, but we're still transferring a proton. In this case here, we have a hydrogen that's covalently bound to this chlorine, okay? And we have a lone pair on methanol. So it's an organic compound, it's not water. And it can do the exact same. It donates a pair to form a new sigma bond to that hydrogen. The old sigma bond gets transferred to the chloride. Remember, this is a weak base, so it transfers back to its chloride ion, and we end up with our oxonium ion. So it's the organic equivalent to the hydronium. So this is not classically Arrhenius. But it is classically Bronsted-Lowry, but it also follows all the rules of Lewis acid, Lewis base. So I think if we look at everything as Lewis acid, Lewis base, we can actually apply both of those other acid theories to it as well. Okay, so let's think about things, not just acid and base, but now let's think about Lewis acids and Lewis bases. Okay, so some good things to look for when you're looking for a Lewis base is, number one, does it have an anion? That makes it a pretty good Lewis base. Okay. Number two, does it have lone pairs? That'll make it a Lewis base as well. Okay. Now we also have to look at as the electronegativity decreases, the base strength will increase, because remember, the acid strength decreased as we increase the electronegativity. So we see the opposite trend in these Lewis bases. Okay, so our halides, 4 lone pairs, negative charge, it can act as a Lewis base. But remember, those are very weak Bronsted-Lowry acids. Very weak Bronsted-Lowry bases, because they're happy as ions. They have a high electronegativity and they can spread their charge out. The next thing we have is neutral oxygen-based species, like water, methanol, or ether. All of these are weak Lewis bases because those lone pairs still can contribute. Okay. Now, moving to nitrogen, right here, nitrogen has a lower electronegativity, meaning it's less acidic, which means it's more basic. So our neutral nitrogen species with a lone pair on them, notice they all have a lone pair, makes it a good, strong Lewis base. Now, stepping it up one more, we have a charge and an oxygen is an even stronger Lewis base. And if we have a nitrogen with a charge on it, it is also even stronger. So think about, first trend is electronegativity in neutral species, and then electronegativity in negatively charged species. So that means the strongest bases we're going to be using are things like this right here, where that. So just to kind of ponder the future, if that was a chlorine and that was oxygen, the next oxygen was nitrogen, and that got stronger. Ooh, what's next over from nitrogen? It's carbon.
I have a question.
Yes.
So the strongest Lewis bases have the most potential to donate their electrons.
Yes. They will abstract less and less acidic protons. So imagine if you had to use a strong acid to protonate these, you have to use kind of a strong acid to protonate these. This can be a weak acid. This can be a very poor acid. And now this can be something you wouldn't even consider acidic, because it's so strong, it's going to pull the proton off anything.
So they're inversely related to strong acids, or to acids.
Correct. So your strong acid become a very weak base. Your weak acids become very strong bases.
Thank you.
It's good delineation. Okay, so what are we looking at time-wise? We're fine. We have 12 starting. Okay. However, there's not always this opportunity when we're going to just have a neutral species attack the lone pair or something like that. we also have an opportunity to have things that have a charge on them, like a cation. That cation is a Lewis acid because it wants to accept electrons to make a new bond. Okay, so now we can have organic cations act as Lewis acids, willing to accept the lone pair from even weak bases to make a new sigma bond. Okay, so in this case here, we're going to have a cation that we call a carbocation. It's basically a positive charge on a carbon. Okay, and we're going to use these a lot. So this is a very good example of a Lewis acid that's not what you would consider an acid or a base. That Lewis acid wants to accept a lone pair. This bromine has a negative charge on it. And so we have a positive charge and a negative charge. And when we share those electrons, the charge goes away. We end up with a neutral species and a new sigma bond. The cation was the Lewis acid. The anion was the Lewis base. Okay. All right, so questions on that. So this is why Lewis acid, Lewis bases are used more in organic chemistry, because we don't have to worry about water. We don't have to worry about transferring a hydrogen. There's actually no transfer of hydrogen here to make this reaction. All we did was the acid accepted electrons. Okay, and that is the end of acids and bases. Questions about Lewis acids and bases?
Could you just briefly go over again the resonance delocalization?
Sure, I can do that. In fact, there's a great let's see, right here. Let me go ahead and erase the stuff I have here. Okay, so the idea here is that just like in the idea if the ion's big and fluffy, it can stabilize more charge, right? Because it has a greater surface area. Hang on, I'm trying to admit somebody here. There we go. Just like when you had a fluoride ion versus an iodine ion, it's easier to stabilize that charge over that surface area. In the case of these resonance structures, we're actually stabilizing the charge over more than one atom by looking at the Lewis dot structures. Okay. So in this case here, if we drew a correct Lewis dot structure for our acetic acid, it would look something like this. And then if we took one of those protons away, that means this lone pair gets put back on that oxygen. The hydrogen goes away without the proton, without any electrons. It's been donated by the other the other base. So now we have a Lewis dot structure, a valid Lewis dot structure with a formal charge of -1. However, why does it have to be down here and not up here? Well, there's no reason, because we can draw a resonance contributor to that by just kicking electrons in here and out here. This is a valid Lewis dot structure, a valid resonance contributor. So that means that, you know, we spend half our time here, so it's half a negative charge there, half a negative charge there. So that's easier to stabilize because it's only part of the negative charge is on either oxygen at any one time. In contrast, if we have something where the ion has to stay on that oxygen, it means that it is going to be less acidic because there's that has a full plus, there's a full -1 charge on that oxygen, and it's going to be easier for it to just stay protonated. Does that answer your question?
Yes. So basically, I just want to make sure that's right. So if they have more than the more resonance structures they have, the more stable and acidic they are?
Yes.
All right, thank you.
And for the organic materials in particular, this carbonate ion or this acetate ion is definitely the number one that does it. Okay. All right. Let's go ahead and shake it off a little bit. I'm going to drink some green tea here. Okay, so think about any more of these questions here. We're going to go ahead and go over to chapter 3. Okay, So acids and bases are important, especially the Lewis acids and bases. Once we get into reactions and reaction mechanisms, trying to figure out what's going to happen a lot of times comes down to that acid-base reaction. We're going to learn there's 5 different things that can happen in a reaction, and that acid-base reaction, typically the Lewis acid-base reaction, is one of them. Okay. So make sure you go ahead and do that homework. I see some people have already done chapter 2 homework, but you can go ahead and do that homework and try to get that straight in your head. Strong acid, weak base, those 4 factors, and Lewis acid. All right, I'm going to transition now to alkanes and cycloalkanes for the remainder of today's lecture. So now we're getting into organic chemistry, things that we're going to look at. We studied the nature of the bonds, and we figured out that the hydrogen-carbon bond is a nonpolar bond because their electronegativities are close. But there's a lot of different ways we can attach them. And by doing hybridization, we can actually have single bonds, double bonds, or triple bonds. So we're going to talk about the nature first of the carbon, hydrogen, and carbon-carbon single bonds. Okay, so the general term for just any compound that composed of only hydrogen and carbon is a hydrocarbon. Okay, hydro for hydrogen, carbon for carbon. So that means there's only hydrogen and carbon on there, and there's still millions of ways to hook those things together. Okay, so it's not that it's boring, it's just that that's what they are. Now, if there are no double bonds in the system, it's what we call a saturated hydrocarbon. What that means is that if we had a double bond, we could actually add more hydrogen to the system to get rid of that double bond so that it would be unsaturated. Okay, so that's what if you think about saturated and unsaturated fats, that's where saturated fats are where they've taken the double bonds away. Unsaturated fats still have double bonds available to them. So when we have completely single bonds, we call it a saturated hydrocarbon. The next thing we have is the more technical term. So hydrocarbon and saturated hydrocarbon are generalized terms, but when we start naming these compounds, we call them alkanes, K-A-N-E. The A-N-E tells us we only have single bonds, okay? So that means we have a saturated hydrocarbon that are arranged in a chain, and that's sometimes called an aliphatic hydrocarbon, okay? Because the opportunity to create a different structure called an aromatic structure, this is what we call the saturated hydrocarbons or alkanes. Okay. So that's just a little basic. Now, within that group of hydrocarbons, we actually have 4 classes. So we have the saturated, which are the alkanes right here, and they consist of only carbon and hydrogen bonds, like found in here, and only single bonds. Okay, and so the end of those names are going to contain A-N-E, always. A-N-E are going to be in those ends of those. Now, the next thing we have, division, is unsaturated, meaning we have at least 1 pi bond in the system, okay? And the simplest of those are the alkenes, okay? So the alkenes, E-N-E, tells us that we have a double bond in their system, and so all the names will have E-N-E in the end of it. So that means at least 1 double bond in the system. Okay. However, if you have 2 pi bonds over a single sigma bond, you have a triple bond, and that's a different functional group. That different functional group is now the alkynes, Y-N-E, okay? Which means all the names are going to end in Y-N-E. That's telling you that you have a triple bond somewhere in your system, okay? So A-N-E means you are completely saturated. E-N-E means you have at least 1 double bond. Y-N-E means you have at least 1 triple bond. Okay. Now, there's another group of compounds, and we'll study this. We have a whole chapter on this, actually 2 whole chapters. And what we call these are what we call arenes or aromatic compounds. Okay. So these are compounds that have alternating single and double bonds in rings. Okay. And they have special properties, and we'll talk about that when we get there in chapter 9. But they are called aromatic compounds, benzene-like compounds, or arenes is the general term. So we'll look at those as a separate class. So the first one we're going to talk about of the hydrocarbons are going to be the alkanes, alkenes, and alkynes. Okay, so if we go back to chapter 1 and think about our molecular geometry is controlled by the fact that we have sp3 hybridized carbons, which means the hydrogens or the carbons are all going to be approximately spaced 109.5 degrees apart. That's because they're blended all three P's with the S, and they're all equal in shape and size. Okay. So another thing that we would look at that, notice this is kind of drawn like a zigzag here. Okay. Remember that when we do these line drawings here, that each end is a carbon. So our line drawing would look like that right here. And then we filled in all the hydrogens so that you can see it. So it's just simple straight chain. Now, one thing to note is that that's just a way to draw it. There's nothing fixing it in that position. These bonds can move. All of these bonds right here actually rotate, and we'll talk about that in a little bit. Okay, so alkanes tend to have that tetrahedral geometry around each and every carbon. Okay, so chemists are lazy, so we've come up with a quick way to kind of show us how to abbreviate this by drawing our formulas. And we call this the line formula. Some people call it the zigzag. But it's basically represents compounds without having to draw out all the carbons and hydrogens. Okay. So when we talk about these line angle formulas, each line represents a bond. Okay. So there's a single bond. So if you have one line, it's a single bond. If you have two lines, it's a double bond. If you have three lines, it's a triple bond. Okay. And each line ending represents a CH3 group. So this dot at the end of this line would represent a CH3 group. This dot would represent a carbon bonded to two other carbons. And that would be the vertex, represents another carbon atom. And then the end over here would be another carbon. So by taking this little structure here and saying our line structure is this right here. So we have one carbon bonded to another carbon, bonded to another carbon, and we assume everything else is hydrogen unless explicitly said. So what does that look like in a ball and stick model? The same thing. Carbon bonded, let me change colors here. Carbon bonded to another carbon, bonded to another carbon, but now we're adding the hydrogens. This carbon was bonded to one other carbon, so we have to add 3 hydrogens. This carbon is bonded to 2 other carbons, so we had to add 2 hydrogens to make a total of 4 bonds. And this carbon was bonded to 1 carbon, so we had to add 3 hydrogens to make up those 4 bonds. And then we can just extend these chains out as long as we want. Okay, so 4 carbons, 5 carbons, and they're just going to continue out now. So do we understand that a line is a bond between 2 carbons, and the hydrogens are assumed there based on trying to get a total of 4 bonds to each of those carbons? Okay. So that's the way I'll be drawing these for the rest of the semester. Okay. Yes. Oh, okay. Yeah, there's a comment here about they're really going to make them different by 1 letter. And yeah, that 1 letter is very important in those names. Okay, so if there's any other atom there, it's explicitly called out. So if you have a fluorine in there, it's a fluorine, a nitrogen, oxygen. But if it's not specifically called out, it's a carbon, and all the hydrogens are assumed. Okay, so let's figure out how we're going to name these things. All alkanes, saturated hydrocarbons, have the general formula of whatever number of carbons you have, this N, you're going to have 2 times N plus 2, okay? Imagine in the middle of the chain, you had a carbon with 2 hydrogens on it. And then when you get to the end of the chain, you have to add 2 more hydrogens to make it 4 bonds to bend it. Okay. Every alkane is named for the number of carbons in its chain, okay? The first 4 are a little hard to remember, but after that, it gets pretty systematic, okay? So the first 4 are one carbon is called methane. And so that would be 1 carbon is meth. 2 carbons is ethane. 3 carbons is propane. 4 carbons is butane. Okay. Now above that, it gets pretty easy because you're used to penta, hexa, hepta, octa, nona, deca. Maybe nona and hepta aren't commonly used, but you know. And then once you get to the higher ones, you have un, which means 1, deca. So 1 and 10, 11. Do, meaning 2, deca, 10, 2, 10, 12. Trideca, tetradeca, pentadeca, hexadeca, heptadeca, nonadeca. So you can get all the way up to 19 with this nice little systematic way until you get up to 20, which is icosane. But that's one you'll have to remember. So it's these first 4 right here and this icosane that you might have to commit to memory. The rest of them follow that pattern pretty well. Okay. So you'll notice there, if we actually calculate out the molecular structure here, it all follows that H's are the carbon plus 2. So for methane, it's carbon of 1 here. So that's 2 plus 2 is 4 hydrogens. They'll all follow this. If you like algebra, you can go calculate yourself. All right. Okay. So that's for straight chains. However, to get the variety of different hydrocarbon compounds we have available to us, we actually have to start hooking those same number of carbons in different ways. And when we hook the same number of carbons up in different connections, we call those constitutional isomers. So they're isomers, and they're only isomers in the way in which they're hooked together. Okay. So an example of that would be this C4H10 right here. So in our line drawing, we can draw it straight like this, or we can break this bond and move it over here to this middle area to give us this other isomer. Okay. So we have 2 isomers, exactly the same molecular weight, but how do we know they're different? Well, because they're hooked together differently, they have different physical properties. So there's actually a significant boiling point difference between butane, which is in lighters, and methylpropane, which is in refrigeration equipment. So they have different boiling points and different melting points, and they can be used for different things. Okay. So those are constitutional isomers, same atoms, different connections. Okay. So why is this important? Well, because that gives you your variety. Okay, if you only have 1 carbon, there's no constitutional isomer. You just have methane right here. By the time you get to 5 carbons, you can have 3 constitutional isomers. By the time you get to 10 carbons, that's 75 different compounds available to you. 15 carbons, 4,000. And by the time you get to 25 carbons, that's over 36 million different combinations you can do. I would hate to have been the student that had to go and figure out the 36 million different derivatives of this. That might have been very, very painful. Okay. So I said that ANE was very important, that ANE is going to signify that we have that saturated hydrocarbon. Okay. So that means we have 2 parts to that name when we had methane, and we have ethane and propane. The first part we have is what the prefix, okay? That's telling us the number of carbons. This is going to be true for all the naming we do in this class. The number of carbons in the longest chain is going to be that prefix, that meth, eth, but, penta, whatever. If we have a hydrocarbon that only has single bonds, we can use the ANE at the end to signify it's a saturated hydrocarbon. So it doesn't matter how many carbons we have. So we can have 15 carbons. We're going to have pentadeca-ane, pentadecane. So it's the ane is the single bonds. Okay, so questions on that. So the meth, eth, prop, penta, stuff like that, number of carbons in our chain, ane telling us we have a saturated hydrocarbon. Okay, so let's add a couple more rules to our nomenclature to help us move along. The first thing I want to talk about is what we call the parent name. Okay, the parent name is what we're going to name, is going to be at the end of the name, that telling us what the longest carbon chain. That's the longest continuous carbon chain. Okay, so if you put an oxygen in the middle, that breaks the chain. So this is the longest continuous carbon chain. Anything that's off of that long continuous chain, like in a constitutional isomer, becomes a substituent. Okay, so when we have something off of that main chain, so let's say you have 10 carbons along your main chain, making it decane, but then you have one carbon hanging off somewhere in the middle. Okay, that one carbon hanging off in the middle is now still a meth for the one carbon, but because it's a substituent, we're going to put the YL at the end, signifying we have one carbon as a substituent. Okay, so that would give us the methyl substituent. And the broad name for these is alkyl groups. Notice how there's a YL at the end of this? There's going to be a YL at the end of all of these hydrocarbon substituents. Excuse me. I did get a COVID test. It's negative. This cough has something to do with allergies, so sorry. Okay. So in my example here, I said we have a long chain. The longest continuous chain is your parent chain. So we want to start by counting out that. So we go, let's see, right here. We're going to go 1, 2, 3, 4. And if we went up this way, that'd be 5. So that's not very long. But 6, 7, and 8 right there. So we could actually, the longest chain we can get is 8. Okay. So, but we still have one more carbon. We got to identify that one carbon because it's not octane. It's actually has a methyl group on it. So that's one carbon. So we start with our meth. We add the YL at the end to make it a methyl substituent. And then we signify where it is. Okay. Now, a new rule that we want is we want to make sure the substituent is on the lowest number possible. So if we accidentally numbered our system 1, 2, 3, 4, 5, our first substituent would actually be on the 5. Okay, and we don't do that. We want to number it from the other side to make sure our first substituent's on the lowest number. So that's going to give us our answer of 4 is telling us where that methyl substituent is, and octane is our parent chain. Excuse me. So, parent chain is the longest continuous. All the alkyl groups are spread out along that chain, giving you the different constitutional isomers. Okay, so these side chains have some common names, and these are things you're going to have to write down and convert to memory right here. Some of them are pretty easy, like the methyl group is the simplest, the ethyl group is next, and then the propyl group. Once we get to the propyl group, we have constitutional isomers possible. Okay, so when we have a constitutional isomer possible, we have to name it specifically, right? So in the case of this, we have propyl. Notice that's the straight chain, the one that's like this. The isopropyl is actually where you are bonding it to the middle of the chain, not the end of the chain. So that's our first constitutional isomer of our substituents. Okay, so we go from propyl to isopropyl by creating a branch point in that chain. Okay. If we go on to the next one, 4 carbons, simple long chain is called the butyl. Okay. However, if it looks like the isopropyl group in it right here, it's called the isobutyl. Okay. And if we change to a different isomer where we move a methyl group instead of on the second carbon over to the first carbon hooked to the parent right here, we're going to call that sec-butyl. And the reason is the carbon bonded to the main chain is considered what we call primary here, but it's a secondary here. And I'll talk a little more about that later. And then if we have a different isomer right here where we have 3 different things bonded to the carbon bonding to the parent chain here, we call that tert-butyl or tertiary. So these are the alkyl forms you will have to remember. So go ahead and make flashcards or look at there. Oh, by the way, on the Canvas site, there is a nomenclature overview page that covers all of these groups, by the way. So you can use that as a resource. It's under resources, files, nomenclature, review. Okay, so let's add a couple more rules. So we're going to find the longest unbranched chain to make it the parent. That gives us the prefix, the number of carbons on our longest unbroken chain. And because we have a saturated hydrocarbon, we're going to add that suffix -ane. Okay. Now we need to identify all the branched parts that are coming off there and give each substituent a name. So in the case of a methyl group, it'd be methyl. In the case of an isopropyl, it'd be isopropyl. Okay. And we have to give it a number. Okay. So when we give it a number, we're numbering the parent chain from one end or the other to give us the lowest number for our first substituent. If we only have one substituent, we just give it the lowest number. So for example, in this example here, I have a methyl group that I'm trying to identify here. If I labeled it from this side, I would have a 2 as my locating number for my methyl group. If I numbered from the other side, I would end up with a 4, okay? We don't do that. We always try to give it with the lowest locator number possible. So sometimes you might have to number the parent chain from one side and the other side to figure that out, okay? But sometimes it'll be in the middle and it doesn't matter. But the key is you want to make your substituent on the lowest one possible. Okay, so what if we have more than one substituent? Well, there's 2 options here. If they are identical substituents, we can actually say we have 2 of those methyl substituents, and we can call them dimethyl. We just have to show which carbons they're on. Okay. We can have 3 methyl groups and call them trimethyl or 4 tetramethyl. So if they're the same, we can use that di, tri, tetra that we would use traditionally. Okay. But we also want to make sure that we have the lowest number possible. So if we look at the way these are numbered here, if we numbered from this side over here, we would end up with the numbers of 3 and 5. If we numbered from the other side here, we would end up with the numbers of 2 and 4. So the key is you want to put the first substituent on the lowest number possible. Okay. So even though there's 2 substituents here, we're going to start, we're putting the first substituent on the lowest number possible. Okay, and then let's see, I'm confused, the lowest one possible. Okay, so when you're numbering your long chain, you want to take the first substituent and have it at the closest to where you started numbering. So if you started numbering at one end of the chain, is the number for that first substituent lower than starting from the other end of the chain? Okay. Okay. So you typically want to go for whichever gives you the first substituent the lowest number. Okay. All right. So that being said, now we apply the di rule. So we only have 2 methyl groups, so we can say dimethyl. Okay. So the first one shows up on the 2 carbons, so we have 2. The second one shows up on the 4 carbons, so we have 4. But notice we have some punctuation here. Okay. We always separate numbers from each other with a comma. So if we had 5 things, it'd be 2, comma 5, comma 7, comma whatever. And then we separate numbers and letters with a dash. Okay. Now notice the substituent here, there's no gap here. So we actually run our substituent into our parent name. Unless we're describing something about the parent here where we're going to need a number associated with it, it'll always be running together one word. So because we have 2 methyl groups, we have dimethyl. Because this gives us the lower numbering scheme, numbering from this direction here, we have 2, 4 dash dimethyl hexane. All right. So I'm going to do one more rule and then we're going to break and I'll see you on Thursday. The next rule is if you have 2 or more substituents, you list them in alphabetical order, not numerical order, alphabetical order. Okay, so in this case here, we have an ethyl group here, and we have a methyl group. Okay, if we number from this side here, the ethyl group is on the 3. If we number on from this side over here, the methyl group is on the 3. So we have the first substituent is on the same number. However, ethyl comes before methyl in alphabetical order. Therefore, we're going to number it from the side that gives us the lowest substituent first and the lowest alphabetical second. So in this case here, the correct name would be 3-ethyl-5-methyl, and we have a long chain of 7, so that's heptane. Okay, so digest these 6 nomenclature rules, and we're going to add more to them on Thursday. So, and yeah, that is the correct answer on alkyl groups. And so I'm going to go ahead and stop recording. If you want to stay back and ask some questions, go ahead. I'm going to leave it shared so that in case you want to look at something here, got to turn my mouse on and